Question number 5. The diagram shows part of the curve y is equal to x sec hyperbolic square x and its maximum point m. Show that at m, 2x tan hyperbolic x minus 1 is equal to 0, and verify that this equation has a root between 0.7 and 0.8. So the first part of the question is simple differentiation. So we can take u as x using the product rule, and v is equal to sec square x, sec hyperbolic square x, and then so du over dx is equal to 1, and dv over dx, if you were to differentiate this, you're going to get negative 2 sec x sec square x tan hyperbolic x. Of course, you can use chain rule here. So what we're going to do is we're going to try and apply the product rule now. So we have u dv by dx, so that's minus 2x sec square hyperbolic x tan hyperbolic x minus v du, so sec square hyperbolic x, and all of that is equal to 0. Why? Because here at maximum point dy by dx equal to 0. The sec square x can be pulled outside, so this is plus basically. All right, so we have then sec square hyperbolic x into minus 2x tan hyperbolic x, okay, and then plus 1 is equal to 0 after we factor this out. And we can divide, okay, divide by negative sec hyperbolic square x on both sides. If we do this, you end up with 2x tan hyperbolic x minus 1 is equal to 0. Right, so this has been shown. Now we need to verify that there's a root between 0.7 and 0.8 for this equation. So what we're going to do is we're going to let fx, okay, let fx is equal to 2 tan hyperbolic x minus 1. And so what we have then is f 0.7, which is then 2 tan hyperbolic, 2x, 2x tan hyperbolic. So basically now we have then 2 times 0.7 tan hyperbolic 0.7 minus 1. So let us see what we get in our calculator here. So the tan hyperbolic x, so what we have is then number 3 as an option here, 0.7, and of course multiply by 2, multiply by 0.7, which is multiplied by 1.4, take away 1, negative 0.154. So we got negative 0.154. And so for f 0.8, we're going to get 2 times 0.8 into tan hyperbolic of 0.8. And if you were to do this in the calculator, you should be able to get 245. So we have a change of sign over here. This one here is less than 0. This one is greater than 0. So the change of sign indicates the presence of a root between these intervals. For the second part, we need to show that the sum, okay, let me just draw a few rectangles here. So if I look at these triangles here, all these triangles, they've got areas, the sum of the areas of these, not triangles, sorry, the rectangles, the sum of the areas of these rectangles is less than the area under the curve itself. So the area under the curve is basically the integral of this expression here. So what I'm going to do is, they did say that we need to show that the sum here is less than all of that expression. So of course this is our integral. So what we're going to do, we're going to integrate x sec square hyperbolic x, limits going from actually 1 to n. Why? Because if we start from 1 here, we can see right in this diagram that from here the area covered we have to start from 1 for the area to cover all the rectangles here. So let's use integration by parts here, which is not new to you. So u is going to be equal to x, and du is equal to 1, dv is equal to sec square hyperbolic x, and integrate that, should be able to get v as tan hyperbolic x. So we can apply the product, we can apply the integration by parts, and so we have x tan hyperbolic x limits going from 1 to n minus the integral of tan hyperbolic tan hyperbolic x, okay, tan hyperbolic x going from, times 1, of course, with respect to x, 1 to n. Now, if I were to actually substitute the limits here, I'm going to get n tan hyperbolic n minus 1, okay, tan hyperbolic 1. And if I were to integrate this, I should remember this is of the form sine hyperbolic x over cos hyperbolic x dx. And now if we look at this carefully, it's going to end up as ln cos hyperbolic x, because remember this is of the form f prime x fx dx, which is equal to ln fx dx. So it's of that form. So therefore we have then in brackets here ln cos hyperbolic x going from 1 to n. Now, just a question of substituting all our values in there, minus, if I were to substitute n, I'm going to get minus ln cos hyperbolic n, okay, minus ln cos hyperbolic 1. Therefore, now if I were to minus this, okay, this becomes just minus cos hyperbolic n, and then minus minus becomes plus ln cos hyperbolic 1. So let's go further here. N tan hyperbolic n minus tan hyperbolic 1, okay, minus. The minus can become plus, and I can go a bracket here, put a minus here, cos hyperbolic n, okay, plus, all right, let's do the plus here, plus ln cos hyperbolic 1. Good, so n tan hyperbolic n minus tan hyperbolic 1, okay, plus this one, using the law of logarithms, I have ln cos hyperbolic inverse n. The plus can turn into a minus, and I can put a minus ln cos hyperbolic 1 inside, because minus minus becomes plus again. All right, so let's copy that again. Got to be very fast in the exams. This is 1 over cos hyperbolic, which is basically sec, so minus sec hyperbolic n minus, and here the same, you can say ln cos inverse cos hyperbolic 1, cos inverse hyperbolic 1, and so we have then n tan hyperbolic n minus tan hyperbolic 1 a minus ln sec hyperbolic n minus ln sec hyperbolic 1. Okay, we're almost there, and now we need to put this in the proper order. So we have n tan hyperbolic n, okay, plus n sec hyperbolic n, okay, plus n sec hyperbolic n. So therefore we have, okay, we did say that the minus over here, minus and plus becomes plus here. Outside is a plus, outside is a plus. So plus ln sec hyperbolic n, which is the same as this, plus ln sec hyperbolic n, minus, here I've got minus tan hyperbolic 1, so minus tan hyperbolic 1, and finally minus ln sec hyperbolic 1. All right, So now you can see all of that here, which is from here, is the same as this. Therefore, I can clearly say that the sum, okay, of these rectangles areas, okay, is actually less than all of that here. Well, I hope that this has been of some help to you. Take care.